Welcome back to the History of Being Human podcast. I'm the host, Noel Armstrong. The only podcast, as far as I know, that guarantees you twice your time back. I will refund you twice the amount of time you spend listening if you don't learn something or find something to enjoy in every single episode. Contact me at thobhpodcast@gmail.com. And again, as always, thank you to those of you who took the time to give us a rating or a review on the iTunes Store or other podcatchers. Well, once again, I had to call an audible. I had another episode planned. I was actually pretty excited about it, but then something earth-shattering happened. The Standard Model came under threat. The W boson is too heavy. Now, before you lose sleep, or before you turn off this entire episode, let me just say that I saw those same headlines, didn't really understand what they were talking about. I have a very, very weak grasp of particle physics. And this is frankly something I had always intended to rectify. In fact, I've tried several times, but I've never really been able to do it. Part of the problem, I have to admit, is it's very hard to learn something that you think you already know. So from a very young age, at least by early grade school, I thought I understood the building blocks of all matter. Protons and neutrons make a nucleus, circled by electrons, which makes an atom. Atoms join together to make molecules, which make elements, compounds, mixtures, and all of it is the basis for everything that we can touch, feel, and see. And I have to admit, to my shame, that grade school understanding of physics has sustained me through all the years since, through my education and through my life since that time. I don't know if this is a comment on me or our education system or both, but I made it through physics, chemistry, and organic chemistry and actually did pretty well without knowing any more about the Standard Model than I learned in grade school. Now trust me, it's not because I haven't made some half-hearted efforts in that direction. Every time I visit a library or bookstore, I'm tempted to stop in the science section. And I will usually pick up a book and thumb through it about quantum mechanics, particle physics, astrophysics, something like that. Because I realize full well you can't claim to be an educated person in the 21st century without understanding the fundamental particles and forces that shape our world. But if you, like me, have tried to get through any of these physics popularizers, you know it can be difficult. Whether it's Hawking or Krauss or Carroll, it's really hard to get through it. And I'm not saying it's their fault, I'm sure it's my fault. But just for example, last week when the headlines were coming out about these discoveries in particle physics, I decided to take another swing. So I picked up a book from Neil deGrasse Tyson called Astrophysics for People in a Hurry, which is, I suppose, just a nicer way to say astrophysics for dummies. From all the writing on the jacket of this book, you would consider it typical and representative of the genre. A great popularizer, someone who is a brilliant scientist, but who can make difficult concepts relatable to non-scientists. And of course, like every other volume in this genre, it fails spectacularly to do that. I love Neil deGrasse Tyson, but this book is a word salad, stream of consciousness, meandering mess. The only value you would get from this book is putting it out on your coffee table and making people think that you know physics. I kid you not, within the first 30 pages, it had wandered from the Big Bang to the biography of Max Planck to the abundance of carbon in the universe to asteroids that destroyed the dinosaurs to the reality of antimatter to Einstein's matter-energy conversion equation. In a word, it was all over the map. It was the ultimate game of nerd inside baseball. And again, I'm sure the problem was me. I don't mean to be too hard on Neil deGrasse Tyson. I'm sure he's a lovely human being. But either he just plain knows too much and can't keep it all organized on the page, or this book was written as a pastiche by an editorial committee. I suspect the latter. But again, my point is simply to say that these are difficult books typically to get through. I would wager a very small percentage of people who bought A Brief History of Time have read A Brief History of Time. It's kind of like the science equivalent of James Joyce's Ulysses or Wittgenstein's Tractatus. When I first began this podcast, one of my stated aims, one of my mission statements was that I was going to try to resurrect sense and meaning from the dust of a billion factoids. Because I think actually learning and remembering things is rewarding. It's fun. Now I have to admit, I get just as caught up in the details and the fun little minutiae of various stories as anybody else. But I want to try to make things make sense for myself as much as for you all, the listeners. And there's probably no topic where that's going to be more difficult than in physics. And yet, I believe particle physics, an understanding of the fundamental building blocks of reality, is absolutely essential to understanding and comprehending who we are and where we came from. It's a sine qua non. Now that term sounds so pretentious it makes my hair hurt, but it's a great term. Sine qua non, without which not. An essential ingredient. Understanding particle physics is an essential ingredient to understanding who we are and where we came from. And so today I'm going to attempt to tackle a little bit of the standard model of particle physics, a very small amount. My goals are very modest, so I think I can succeed. You don't have to remember every fundamental particle and force by name to understand the general concept. I look at it kind of this way. You don't have to know every species of bacteria and every virus to understand the germ theory of disease. To get the picture that tuberculosis, for example, is not caused by bodily humors running too hot or too cold, or qi not flowing in the right direction through the fourth meridian. And to also understand, for example, that you don't fight the bubonic plague by placing your children in the hands of a Moloch idol, or whipping your back with a cat o' nine tails, because you get the general picture that there are microscopic organisms that can be prevented or fought in certain ways. And my goal with this series is similar to that. With this episode on particle physics, I just want to put a picture in your mind of how things work. Kind of a skeleton, a framework where you can hang the rest of the little bits of information that come your way throughout the rest of your life. I'm very curious to see if I'm going to succeed at this. So, write me at thobh@gmail.com. Let me know how I do. Let's start with the biggest picture question possible. That is, what is particle physics? Particle physics is the branch of physics that deals with the nature and interactions of subatomic particles, specifically fundamental particles, particles that you can't break down into any other particles. So it's the physics of the smallest possible particles of matter and energy out of which the universe is built. The questions that particle physics attempts to answer are very ancient questions. From at least the time of the pre-Socratics, there have been more or less naturalistic attempts to decide what we are made of. What is the basic building block of reality? The first of these pre-Socratics was Thales. He believed and posited that water was the fundamental substance out of which everything else came. After Thales came Anaximander, who said, no, it's not water. It's actually an undefined, unlimited substance without any qualities whatsoever. Kind of reminds you of the tohu bohu spoken of in the book of Genesis. Well, Anaximenes wasn't buying either of their stories. He said that the first principle, the fundamental building block of all reality, was air. Everything, he said, was made of air. Heraclitus said, nope, it's all fire. Everything's in flux, and fire is the fundamental building block of all reality. The point is that the very earliest proto-scientists were preoccupied with the elemental substance, the underpinnings of all reality. In many cultures, they believed that there were 4 fundamental substances, and you've heard of this, the earth, air, fire, and water. And from these 4 elements, they attempted to explain all of the complexity we see in the universe. One school that you will hear quite a bit about is another school in ancient Greece, and that was Leucippus and his pupil Democritus. They are known as the atomists. Some would say these two were way ahead of their time, proposing that everything in the universe was made of either the atoms or the void. And it's this ages-old search for the fundamental building blocks of reality that particle physics concerns itself with. And over the centuries, using progressively more powerful tools of observation, scientists have been able to look into smaller and smaller distances, and they've converged on a picture of the fundamental particles and forces. And by fundamental, they mean, again, particles that cannot be broken down any further. And what they've ended up with is what is known as the standard model of particle physics, a model that has predicted with amazing accuracy the results of literally hundreds of thousands of experiments. According to the Cambridge physicist David Tong, I'll quote him, he says that this theory is unmatched anywhere in science. The current model of particle physics is the most successful scientific theory ever. So when they call it the standard model, they don't mean like a standard package on the car, something that's really basic and needs an upgrade. No, instead they mean it in the sense of setting a standard of quality and reliability and reproducibility of its predictions. And just to re-emphasize what David Tong said, the standard model of particle physics is the most successful scientific theory ever. So just to review, particle physics is the branch of physics that deals with the age-old question of what is the fundamental building block of reality? What are these building blocks? Over time, scientists have come up with the standard model of particle physics. This is the model we'll be drawing from today. It's a model that has been tested in hundreds of thousands of experiments and has predicted the outcome of those experiments with amazing accuracy. And at the biggest picture level, the standard model of particle physics is pretty darn simple. There are 12 matter particles, 4 force particles, and one very unique particle, which has been called the God particle in a famous book, which we will have to get back to. But let's talk about the two big divisions first. There are the matter particles, which are called fermions, and there are the force particles, which are called bosons. When I try to remember that, I just said that matter is firm. So fermions are the matter particles. Now they're actually named after Enrico Fermi, but this works for me. Matter is firm. Fermions are matter particles. Bosses are forceful. So bosons are force particles. So let's start with the fermions, possibly the easiest to understand. What is it that makes a fermion a fermion? Well, if something is firm, this is a good way to remember it, you can't have two of them in the same place at the same time. That's the rule with fermions. No two fermions can occupy the exact same state in the same place at the same time. If you have a one-car garage, and you already have a car filling the one-car garage, you are excluded from parking another car in the exact same space. You and I are excluded from occupying the exact same seat on the exact same chair at the exact same time. Roughly, that's what's called the Pauli exclusion principle. Fermions, being matter particles, obey the Pauli exclusion principle. You cannot have two of these fundamental matter particles, these fermions, in the same place, in the same state, at the same time. I realize that sounds trivially obvious. Fermions, being firm, if you want to use our little memorization trick, hold their space and are therefore the building blocks of matter. There are, as I said, 12 fermions. But everything you see around you is comprised of just 3 of those fermions. Think about how beautiful and elegant and simple that is. 3 matter particles, 3 fermions make up the mother who raised you, the car you're driving, the gas that's propelling your car, the hands you're holding the steering wheel with, the clouds over your head, the sun in the sky. All of it is just 3 matter particles, 3 fermions. And I know you're dying to know what they are, unless you already know. They are the up quark, the down quark, and the electron. Going back to that model that I learned in elementary school about protons and neutrons. Well, quarks are what make up protons and neutrons. Each proton is made of 3 quarks. The proton of the atom has 2 up and 1 down quarks. The neutron has 1 up and 2 down quarks. So the up quark and down quark come together to form the proton and the neutron within the nucleus of the atom. The electron is a fermion by itself. It's not made of anything else. It is properly fundamental and basic. And so between those 3 fermions, the up quark and down quark, which make up the nucleus, and the electron, which circles the nucleus, we have atoms. And those atoms are responsible for the entire physical universe you see around you. If you remember just that much, that there are 2 general categories, fermions, which are matter particles, bosons, which are force particles, and that 3 of those fermions are responsible for the physical universe, you know more than I knew for, 40 years. So even if we stop here, which probably many of you are going to do, we've learned something. We have to admit we've learned something. But for you, a few brave and stalwart masochistic souls, let's plow on. Let's push forward. I want to take just a brief interlude. If you want to tune this out, that's fine. But I do want you to understand the term hadron. You'll come across the Large Hadron Collider as that particle accelerator, the largest in the world. Well, you might wonder what these hadrons that it's colliding are. Well, very simply, a hadron is two or more quarks joined together. So is the proton in the atomic nucleus a hadron? Yes, because it is two up quarks and one down quark. It is three quarks joined together. It is a hadron. So a hadron is not a fundamental particle. It is two or more quarks joined together. And that is what the Large Particle Accelerator smashes together. Those are the hadrons that it collides. And so now let's get back to the standard model. Let's get back to the fermions. So far we've talked about 3 of the 12 fermions: up quark, down quark, and electron. There's another fermion that's kind of unique. It's not like the other fermions, and it's called the neutrino. Neutrinos are weird fermions, matter particles, because they have very, very, very low mass and they barely interact with anything. They essentially, for all we know, just rip around the universe, passing through space and the atmosphere and your body and pretty much everything physical. Estimates are that every 1 second, 100 trillion neutrinos pass through your body. Most of these neutrinos come from the fusion processes in the sun, but some of them have been around since the beginning of the universe almost. So now we have 4 matter particles, 4 fermions: the up quark, down quark, electron, and neutrino. Once you know those, getting the other 8, understanding the other 8 is actually pretty simple, because every one of those 4 quarks that we've already learned has 3 generations. So the electron has 3 generations, the up quark has 3 generations, down quark 3 generations, and the neutrino 3 generations. These generations act like the up quark, the down quark, the electron, and the neutrino. The only difference is they're much, much heavier. So for example, if you act a certain way, then you have a child who acts that same way. Say you're 150 pounds, your child weighs 30,000 pounds. Then they have a child that weighs 450,000 pounds, but you, your child, and your grandchild, aside from being so different in mass, all act pretty much the same way. That's roughly akin to the generations of fermions. So, for example, with the up quark, there are 2 other generations of quarks that are kind of like it. They act like it, but they're heavier. And the term that they use for these different quarks is not types or categories, it's actually flavors. So there are 2 other flavors of quark that are kind of like the up quark, and they are called the charm quark and the top quark. Let's go to the down quark. The down quark has 2 other flavors that are kind of like it, kind of taste the same. Those are the strange quark and the bottom quark. These names you don't have to remember, of course, but they are easy to remember. All you have to remember is that up is the charming top and down is the strange bottom. So come up with whatever mental image you want to. I know I have my own, but up is the charming top, down is the strange bottom. And before you realize it, we have named 8 out of the 12 quarks. Electrons and neutrinos also have their own generations. They're not as cleverly named though. The electron family includes the electron, the muon, and the tau. The muon is heavier than the electron, and the tau is the heaviest. And once you know that, you also know the neutrinos, because there is the electron neutrino, the muon neutrino, and the tau neutrino. They just borrow the names from the electrons and apply them to the neutrinos. And now, of course, you're going to ask, why don't we see these 8 other types of quark in nature? Why do we only see the up quark, down quark, and the electron and know about the neutrinos? Why don't we see their heavier relatives? Well, if your child weighed 30,000 pounds and your grandchild weighed 450,000 pounds, how stable would they be? How long would they live? Well, it turns out that all of the fermions, except for the up quark, down quark, electron, and neutrino, are very unstable. You can create a charm quark or a top quark in very high energy conditions, but they're actually very unstable and they will soon decay back down to an up quark. They exist and we can find evidence of them, but only in particle accelerators like the Large Hadron Collider we just talked about. So those are the matter particles, the fermions: up quark and its generations, down quark and its generations, electron and its generations, and the neutrino and its generations. Why are there 3 generations for each of these fermions? The answer is actually very simple. No one has any idea. Figure that out and win a Nobel Prize. So now that you have a firm grasp and fully comprehend all of the fermions, all of the matter particles, let's move to the force particles, the bosons. The standard model of particle physics accounts for exactly 3 forces. These forces are the strong force, weak force, and electromagnetic force. You'll notice gravity is missing from that. Gravity is another force. It is not accounted for by the standard model. We'll come back to that in a little while, but let's talk about the forces that are accounted for by the standard model. First, let's talk about the electromagnetic force. That's the force that we can understand the best, probably, because it is just what it sounds like. It is electromagnetism. It is the force that acts on any particle that carries a charge. Quarks carry a charge, and so the electromagnetic force acts on quarks. Electrons obviously carry a charge, so electromagnetism operates on electrons. Now, for each of these fundamental forces, there is a particle, a boson. The boson that corresponds to the electromagnetic force is called a photon. So the first fundamental force particle that we're going to talk about, the first boson, is the photon. So really, what we call electromagnetic radiation could be described in terms of a stream of photons, massless particles, each traveling in a wave-like pattern at the speed of light. I'm not even going to try to unpack that. That would probably take longer than everything I've covered so far. So all I'm going to say is that the photon is the boson of electromagnetic radiation. That is the fundamental force particle, and it acts on any charged particle. So it acts on quarks and it acts on electrons. It does not act on neutrinos because they are neutral. Let's move on now to the next fundamental force. That next force is called the strong force, or the nuclear strong force. Now, there are a few things we need to say about the strong force. The first is that it is indeed very strong. It is 100 times as strong as electromagnetism. The next thing is that the strong force acts only at very, very small distances, subatomic distances, and it acts only on quarks. It does not act on electrons or neutrinos. It acts only on quarks. Unlike electromagnetism, that radiates out in all directions from the electron, the strong force goes out as almost like a little wavy tubule, a little finger from one quark reaching out to another quark of a different type. And they always succeed in finding another quark. You never see quarks in isolation. They're always bound to other quarks. That's because of the strong force. And of course, it would have to be stronger than electromagnetism. Otherwise, the electron circling the nucleus would be able to pull the nucleus apart. It is possible to break the bonds that bind these various quarks together. In other words, it's possible to break the bonds of the strong force. That's what happens, for example, when a large atom is smashed into 2 smaller atoms. That breaking of the strong force releases a huge amount of energy. That's what's called nuclear fission. That's responsible for the atom bomb of Hiroshima and Nagasaki fame. Thank you to Dr. Oppenheimer and Dr. Fermi, after which the fermions are named. The particle of the strong force is really easy to remember. It's called the gluon. Glue is strong at holding things together. The strong force particle is the gluon. That is the boson of the strong force. So look how far we've come. We only have a little ways left to go. We've already talked about all 12 of the fermions, the matter particles. We've talked about 2 of the force particles, the bosons. We've covered the gluon for the strong force and the photon for electromagnetic radiation. The last force that we're going to talk about is kind of the hardest to understand, so I'm not going to go into it in any depth. It's called the weak force. And whereas the strong force is responsible for gluing things together, the weak force is responsible for decay. Basically, what the weak force can do is take an up quark and turn it into a down quark. It can also take a down quark and turn it into an up quark. I know, it's confusing. But let's look at it this way. In the nucleus of an atom, you have protons and neutrons. A neutron is 1 up quark and 2 down quarks. If it's acted on by the weak force, it can flip one of those down quarks into an up quark. It can turn a neutron into a proton, in other words. That's what's responsible for beta radioactive decay. When a neutron is acted on by the weak force, and one of its down quarks flips to an up quark, energy is released. Specifically, every time a neutron is turned into a proton, one electron and one neutrino are released. Now, I know what you're thinking. Weak force, flipping one neutron into one proton, releasing one electron and one neutrino. Big deal. Pretty weak mechanism. But actually, the opposite is the truth. This is the very force that powers the fusion reaction of the sun. It is the weak force acting on protons and neutrons in the sun that makes life on Earth possible, that gives us the energy for life on Earth. Remember I said earlier, trillions of neutrinos pass through your body every single second. This is where the vast majority of those come from these fusion reactions in the sun. And so while the weak force may not be as strong as the strong force or even the electromagnetic force, it is very, very strong in its effects. Now, earlier I said that there were actually 3 forces accounted for by the Standard Model: strong force, weak force, electromagnetic force. But there are 4 particles associated with these forces. That's because the weak force has 2 particles associated with it. There is the W boson and the Z boson, both of which are fundamental particles of the weak force. So I think we should pause just for a moment and pat ourselves on the back to see how far we've come. We have learned a very big picture overview of some of the key components of the Standard Model of particle physics. And yes, I understand this is a dramatic oversimplification. To really understand particle physics, we would have to speak in quantum field theory terms, and we're not going to do that. But we have learned 12 matter particles, 12 of the fundamental building blocks of all matter, and those we called fermions. We have learned 4 force particles associated with 3 forces, and those we called bosons. There's really only one key component to make this picture, this overview, complete. That is the Higgs boson, the one that has been popularized as the God particle. And I struggled with how much to cover this, how much depth to go into, and I realized very quickly I was way out of my depth. So I'm just going to call it this. The Higgs boson is the fundamental particle which, through the Higgs field interaction, is responsible for giving mass to every massive particle. Without the Higgs boson, no fermion would have any mass whatsoever. So when you think of the Higgs boson, think of mass. And one thing that's fascinating about the Higgs boson is it was only a theoretical construct predicted by the Standard Model. And it was this way for years or even decades. It wasn't until 2013 that the Higgs boson was identified, which was, of course, just another victory for the predictive value of the Standard Model of particle physics. And I will say that even though it is very successful, it is neither complete nor perfect. One of the most important shortcomings of the Standard Model is it doesn't include one of the fundamental and ubiquitous forces in nature, and that is gravity. Standard Model does not account for gravity. And one reason for that is that gravity is so weak at the subatomic level that you don't even need to take it into account to have very accurate prediction. Just how weak is gravity? Well, it is about 10 to the 40th power weaker than electromagnetism, and about 10 to the 42nd power weaker than the strong force. It is so weak, in other words, that it is either insignificant or trivial at the subatomic level. There is another shortcoming of this presentation of all these particles, and that is, it might tempt you to think of the universe as a bunch of isolated dots separated by vast regions of space. In fact, that's what I grew up thinking the universe was like. There was a little tiny dot here, huge space, and then a little dot there. Total void between these dots, such as between the electrons and the nucleus. Well, that's really not true, because the Standard Model is actually written in a language we call quantum field theory. I alluded to this earlier. Quantum field theory teaches us that at the most fundamental level, reality is not made up of particles. If you look through a powerful enough microscope, you would not see a bunch of dots moving around. Instead, there are fields. Fields are these fluid-like energy patterns that interact with each other, and when they interact, they give rise to the particles that comprise the entire physical world. But that's a very difficult thing to visualize, difficult to talk about, and so we talk in terms of particles, fermions, and bosons. Another shortcoming of this standard model is that it gives no account of dark matter and dark energy. It gives an account of a very small percentage of the universe, which is the matter and energy that we see, that we can detect. The only parts of the universe that we can detect are those that interact with electromagnetism. Dark matter does not interact with electromagnetic energy. We cannot detect it. We can't see it. The standard model of particle physics gives no account of dark matter and dark energy. And those account for, by far, the greatest mass of the universe. So that's another failing or shortcoming, if you want to call it that, of the standard model. Doesn't mean it's wrong. It just may be incomplete. So that brings me to the conclusion of this episode and what got me here in the first place. The headlines about how the standard model is under threat. The weight of the W boson, it turns out, is 0.1% off of expected values. A team of scientists went through for years and years data from a particle collider, and what they came up with was that the expected weight of the W boson did not match reality. It was 0.1% off. That might not sound like much, but if verified, if that's the fact, it would call into question the formulas, the equations of the standard model of particle physics. I will just say the jury is still out on that. Many people are reluctant to see a beautiful theory killed by an ugly fact, in the words of Thomas Huxley. So they are reluctant to say that this one published paper blows up the entire standard model. There will be those who try to revise the standard model and those who try to prove that they were wrong in the way that they evaluated the data, so this standard model still holds. And I have no idea how that's going to turn out. Suffice it to say, every 5 or 6 years, somebody publishes a paper claiming to blow up the standard model, and they have not done so yet. This concludes this episode of the History of Being Human podcast. Thank you to those of you who I'm sure are the stalwart few who were able to power through this entire episode. I hope I've added to your understanding and not just thrown more argle-bargle into the universe. At the very least, I hope you can throw down at the next social event or cocktail party you're at. If you say something that makes you sound ignorant or somebody makes you feel stupid, just whip out a fermion or a boson. Instant redemption.